Hey guys, this is Carrie, and in this video we're going to be doing homework number 7. So let's take a look at problem number 1. So let f of x equal a times b to the x power plus c, where a, b, and c are constants. Which of the following represents exponential decay? So if we think about building these exponential functions in the applications that we've encountered, we often encounter things like starting with $10,000. And then it grows by, I don't know, 7% or whatever. And the way that we figure out the equation for these problems is we say, okay, the amount as a function of the time is start at $10,000, then we're going to be multiplying by, well, if it's growing by 7%, that means each successive year we have 100% plus 7%. We'll have 107% of what we had the year before. That would be 1.07 as a pure decimal to the t power, and that's how the equation would look like. We can tell that this equation is exponential growth because this number here, 1.07, is bigger than 100%. If it were decreasing, this would be less than 100%. So what we need for decreasing exponential decay, we need b to be less than 100%. And what that would mean is b is less than 1, because when we do the division by 100 to convert it into a decimal, 100% gives us 1. So b is less than 1. A student is graphing the function f of x equals log base 3 of x minus 2. So the way that we read this, just to be clear about what we're saying, is log base 3, because this little bottom number is called the base, of x minus 2. So the way that you input this into your calculator is you would type log of x minus 2. So you do log of the thing that you're taking the log of, and then you divide by log of the base. After inputting the calculator generates the table below. Based on this function, based on the table below, what is the equation of the vertical asymptote of this function? So we know with log graphs that log graphs don't actually get to hit the entire grid. There's part of the grid that they miss, and that part of the grid causes an error. So the vertical asymptote is going to be the boundary between error and non-error. It's going to be the first place that you encounter an error. Now there's a temptation, I think, when you're looking at the table to think, oh, this is the first place we see an error because it looks like it's the first. But in reality, we're working from the non-errored entries back. So this is the first value where we hit an error. So since we hit an error at x equals 1, this is the equation of our vertical asymptote. And when we graph it, it will be a vertical line passing through the x-axis at 1. Next up, to completely sketch the graph, we can sketch those points. So we have 2, 0, 3, 1, 4, 1.5, 5, 2. And plotting those points gives us a section of the graph, but we need to remember to show the graph goes on forever, and then also show that it approaches the asymptote forever. Okay, so we've got our function graphed. And we can tell that it matches the table because in the negative and 0 region, this part over here, we have an error because the graph never appears on that side of the grid. You invest $25,000 in an account that earns 9% yearly interest. If interest is compounded quarterly, that means 4 times per year, because quarter is like a fourth, 4 times per year. Then write an equation for the value of the investment after t years. So the way you want to do this is if it goes up by 9% per year, quarterly means instead of getting that 9% all at once, we get that 9% in 4 chunks. So each of those chunks is going to be 9% divided by 4, which I believe is 2.25%. So now we get that 2.25%, and this is how much it's going up by each quarter. So the equation will look very similar to the equations we structured before, but A of t is equal to 25,000 times, okay, if it's going up by this, then we really have 100% plus 2.25%. That gives us 102.25%. That gives us 1.0225 as our multiplier. And because it's being compounded 4 times per year, that means it's 4 times the number of years as the exponent because it's compounded more frequently. than just yearly. This one is going to be really similar in structure, but because it's compounded monthly, that means 12 times. So the percentage is going to be 9% divided by 12, which is 0.75%. Is it? I hope it is. Yeah, I think it's 0.75%. And then that's going to be A of t is equal to 25,000 times 1. Let's do the math over here. 100% plus 0.75%. That gives us 100.75%, which converts to 1.0075 when we do our division by 100 to make it a decimal. Here the exponent is going to be 12t because it's compounded 12 times each year, so 12 times more frequently. Calculate the value of each of these after 5 years. So to do this, you just plug in 5 for both of the t values. I'm going to let you guys do that one. For problem 4, you invest $2,000 in an account that earns interest at a yearly rate of 6.8%. If the interest is compounded semi-annually, twice per year, then do each of these things. So we get the value as a function of time is equal to 2,000 times, to get the multiplier here, since it's being compounded twice per year, if it does 6.8% in 1 year, then it will do half of that each time if we're compounding it twice. So we split this into 2 chunks. So we get 3.4% the first time, and then 3.4% the next time. So then we're going to have 100% plus 3.4%. So it's growing by 3.4%, which gives us a multiplier of 1.034 as a decimal. And since it's compounded twice per year, we're going to have 2t as the power because it's compounded twice as frequently. For part B, using your answer to part A, how long will it take for the investment to double in size? This one is worth seeing out because it's interesting how logarithms come up in this case. So if we want it to double in size, that means the value is going to be 4,000. Now we need to solve this equation for t, so we divide by 2,000 on both sides. That gives us 1.034, to the 2t is equal to 2. The next step to solve for t is we need to cancel out a base of 1.034. So we do log base 1.034 on both sides. When we do logs cancel bases. That gives us 2t on the right-hand side equals log base 1.034 to 2 of 2. And I saw a lot of students, or I heard today a lot of students concerned about which do you put in the calculator. I think if you're taking careful steps here and putting the entire things when you take the logs, rewriting the expression so that it looks as it should for this side, then it's apparent which goes in the calculator first. So it should be 2t equals log of the big number 2 divided by, that's not division, divided by log of 1.034. And so doing that on a calculator, I have to change over to Desmos. Log, I think log is in miscellaneous, yeah. Log of 2 divided by log of 1.034. Close the parentheses, 20.73. So 2t is equal to 20.73, divide by 2 on both sides, and that gives us t equals 10.365. So t is equal to 10.37. Hopefully I did the math on that right, but you guys can tell me if I didn't. And these are units of years because in our equation, t was measured in years. All right, cool. So we're going to continue on with this tomorrow and answering a really interesting question in tomorrow's class, which is what if instead of compounding things quarterly, monthly, daily, we compounded things continuously? So as every instant of every moment of every day, we are getting a little bit of that interest. And it's going to lead us to some really interesting new results. So I'll see you guys in class on Thursday. Good luck on the SATs tomorrow.